Proper time and dilated time. In a special relativity, time and space are relative to you. Let's say we have a spaceship passing by and we have a ground observer, and let's say the trip is our event. Duration of this event as measured by the ground observer is t1 and as measured by the passenger is t2. They won't agree on time. One of them is called proper time and the other dilated time. Let's learn it. I use light clock to tell you what the proper time is. It's a very nice hypothetical tool. Here I have a train and there is a single photon fired downward and will oscillate in between a couple of mirrors in the train. Train of course is moving, but according to the passenger of this train, the motion of this single photon is always vertically upward or downward. Let's say the height of this train is L. The duration of a complete oscillation, the period, is going to be the total distance traveled divided by speed. Speed is the speed of light, you know. In a special relativity, light is in vacuum is always traveling at a constant invariant speed like c. But the distance traveled is 2L here. So the duration will be t naught equals 2L divided by c. Let's do the same experiment, but observe it from the perspective of a person out of the train. This guy is at rest on the station, and the train is moving rightward. Same experiment. This single photon, according to this person, will not travel vertically downward or upward. It has an oblique pathway. You see? Okay. However, height of the train is the same height, but the distance traveled is longer than 2L. Let's say each run is d, so totally it's 2d. But the speed of this photon cannot exceed the speed of light because this is a very important postulate in relativity. So we write the total time for a complete oscillation as measured by the person out of the train as 2d divided by c. We have to accept that downstairs in both cases is c, but upstairs differs. T naught is called proper time and t is called dilated time because t is longer than t naught, because d is larger than L, okay? Proper time is always the shortest time you can measure for a specific event, okay? Look at this event. This event is actually a complete oscillation. The person in the train is always at rest relative to this event, but the person out of the train, no. So we can say the proper time is the time measured according to a person who is at rest relative to the event. Now let's have a relationship between proper time and dilated time. I'll consider just a half of a complete oscillation. So the photon will travel vertically downward according to the person in the train and forget about its reflection. The distance traveled is L, so as we take the time, the duration of this trip, the proper time, the notation of t naught, let's say L is ct naught. C the speed and t naught the time for this trip. According to the person out of the train, the pathway is not vertically downward. It's going to be oblique, you know. D is longer than L. And of course the speed cannot exceed the speed of light because this is the postulate of relativity. So d is going to be ct. T is larger than t naught because d is larger than L. Okay? On the other hand, we know that the train is moving rightward at a speed of v. So meanwhile, in the time that the photon travels from top to the bottom of the train, t, the train will displace also for vt. Now look at this right triangle. The hypotenuse is ct, the vertical side, the height is ct naught, and the horizontal, the base is vt. I use the Pythagoras theorem, and then I write it as ct squared. It is the hypotenuse squared is equal to ct naught squared plus vt squared. This is the relationship between t naught and t. Let's work on its mathematics. Okay, here I have ct naught squared is equal to hypotenuse squared minus vt squared. Okay, in another way. Now let's divide both sides by c squared and then factorize from t naught, factorize from t2, and then finally take a square root. T is going to be something multiplied by T naught. That something is called Lorentz factor. 1 over square root of 1 minus V over C squared, okay? And the relationship between dilated time and the proper time is T equals Lorentz factor times T naught. Let's consider the Lorentz factor first. Lorentz factor is 1 over square root of 1 minus V over C squared. Basically, you see that V is always smaller or maximum equal to C. So downstairs is always something less or equal to 1. So the total fraction, the Lorentz factor, is always larger than 1. The minimum is 1. Okay, when it's 1, when speed is 0 or negligible compared with the speed of light. So we can ignore this term and gamma will be 1. So in the graph, I'm going to plot gamma versus v, the plot starts from 1, okay, when the speed is 0 or negligible. But the limit for the speed is speed of light. It can't get the speed of light except for maybe a radio signal or light. Other real objects cannot go that fast, but however it tends to see. So gamma tends to infinity. Why? Because v over c will tend to 1. 1 minus 1 is almost 0, and so gamma tends to very large number, infinity. So at the speed limit c, gamma goes to infinity. So basically when I write t is equal to gamma times t naught, we know that as the gamma is always greater than 1 or minimum 1, t is always larger or at least equal to t naught. Dilated time is larger than the proper time. So I can say the proper time is the minimum or the shortest time you can measure for an event. The other observers will measure some expanded time, dilated, longer time. Rather than disagreement that these two people have on a single experiment, a duration of a single experiment, this is also the relationship between these two times, okay? Look at this spaceship again. The spaceship travels for a few seconds or a few minutes or whatever you want. The duration of this trip, as measured by the clock in the spaceship, is going to be delta t naught. We believe that this duration is the proper time. The reason, let's say the event is the trip or the embarkation and arrival, whatever you want. This person, according to himself or herself in the spaceship, can see that the spaceship starts going somewhere and then gets destination. Okay, he is always at rest relative to these events. He can see that it starts from this planet and arrives at the other planet. Okay, so he can use a single clock at rest relative to him and measure the duration of this trip at rest relative to him. That's why we say this is proper time. So in other words, proper time is the time measured by a person who is at rest relative to the event. But according to a person on the ground, it's not going to be the same. The reason, because embarkation and destination point will not be at the same place, and actually this event is not at rest relative to this person. So this person has to use a couple of clocks, one to measure the embarkation point, embarkation moment, and then arrival. Okay, the second clock they use has already been synchronized with this clock, and when it's passing by the second clock, it stops working. Then they can compare the two values and find the delta t, the duration of trip as measured by the ground observer. Why the ground observer cannot use a single clock? The reason is that When the spaceship gets destination, okay, very optimistically, you can use a very, very sensitive sensor that can sense it's passing by and then sends a radio signal to this person, okay? And this person will receive the message of arrival. But the question is that, is it immediate? The radio signal immediately can get this person? Of course, no. He cannot be aware of uh, arrival of this spaceship destination. He has to wait for a few moments to get the message from this radio signal, very optimistically. That's why, for immediate awareness, they will use another clock. So he cannot use a single clock. That's why we say this is not proper time, this is dilated time. And you know that it takes longer. So delta t goes for gamma times delta t naught, dilated time. Okay, let's have a definition. When two events occur at the same location in an inertial reference frame, the time interval between them measured in that frame is called the proper time interval, or let's say the proper time. Measurements of the same interval from any other inertial frame are always greater, dilated time. Look at this question. John is flying a plane at zero point 0.9 c. It's a very high speed, 90% of the speed of light, okay? The landing lights, let's say this is the landing light, on the plane flash every 2 seconds as measured in the reference frame of the plane. So John is in the plane and he can measure the duration of this flash for 2 seconds according to him in the airplane, okay, the moving reference frame. Zosia watches the plane go by. Zosia is on the ground, okay? He can observe the same event but not with the same duration. Which one is the proper time? Of course, it's very evident. The person in the spaceship or in the plane can measure the proper time because this guy is at rest relative to the event. But you on the ground are not at rest relative to the event, so you will measure the dilated time. The question is how many minutes or how many seconds is the dilated time? Let's find it. The relationship is delta t is equal to gamma times delta t naught. Delta t naught is given, it's 2 seconds, so let's plug in the values. V at the same time is 0.9 c. And you fulfill the job, you will get 4.6 seconds. Dilated time is always and must be always larger and longer than the proper time, the 2 seconds, okay? 4.6 seconds. Another question. A spaceship travels at a constant speed from Earth to a space station. The space, so let's say this is the Earth and this is the space station, okay? A spaceship is traveling from Earth to the space station, okay? According to the clocks on the spaceship, the journey takes 4 days. So the clocks on the spaceship will measure the time for 4 days. You know, the people in the spaceship are relatively at rest to this clock in the spaceship, and they see the event at rest relative to themselves, okay? So they will measure evidently they will measure the proper time. According to the clocks on the Earth and on the planet, the people here on the Earth or on the planet or maybe the space station are not at rest relative to this event, okay? So they will measure that for 5 days. Part A outline which of these intervals is proper time. Of course, the shorter one, 4. But the reason is not because it is shorter. The reason is that the person in the spaceship is at rest relative to the event. They can use a single clock to measure this duration. But the people on the planet or the Earth, they have to use a couple of clocks, one on the Earth and one on the spaceship. They will tick the embarkation and the arrival, and then compare the two values. That's why it takes longer. Calculate the speed of the spaceship relative to Earth. You know that dilated time is gamma times proper time. Here dilated is 5 days, and this is the proper time is 4 days, okay? You can use the unit of day. It's okay because they will be cancelled. So you don't have to convert it to second. Uh, in the gamma, V is hidden. So we will find the V. Again, as I mentioned, you should plug in the values and then proceed, reverse the fraction. This square root will be equal to 4 over 5. Then you can raise it to the power of 2, and then it's going to be 16 divided by 25. Make a change and then find V to be 0.6 c. V is 60% of the speed of light. Okay? Another question. In a laboratory, an electron is accelerated by a potential difference of 100 kilovolts. So in the lab, you have an electron gun. You shoot an electron using a high voltage. Okay? Its speed then measured by timing how long it takes to pass between two different points measured in the lab as being 5 meters. So we have an embarkation point here and the destination here. According to our measurement in the lab, the separation is 5 meters. Okay? The electron starts from here at the moment t1, then it gets destination at the moment t2. Okay? Is the observer in the electron's reference frame? Observer in the electron's reference frame is the person who is traveling with that, like the spaceship traveler, okay? Or the observer in the lab reference frame recording proper time. Which one? It's clear because the person who is traveling with that can use a single clock and measure the duration of this trip. But on the ground in the lab reference frame, you have to use a couple of clocks, one for embarkation and the other for destination arrival. So you cannot use a single clock. Evidently, the person who is moving with electron will measure the proper time. A rod measured in its rest frame to be 1 meter in length is accelerated to this much speed, 33% of the speed of light. So if a person is at rest relative to the rod, they will measure the length of the rod for 1 meter. Okay? The rod is then timed as it passes a fixed point. So on the ground you have a fixed point and the rod is passing by. Hypothetically, we can have also a passenger on the rod who witnessed the trip from his own reference frame. Okay? Is the observer at the fixed point, the person on the ground, or the observer traveling with the rod measuring the proper time? It's clear. The proper time now is measured by the person on the ground. Why? Because the person on the ground can see that the front is passing at the moment t1 using this clock. When it's passing by, the end of the rod is done and is gone after the time t2. They will subtract these two values and get the delta t. Okay, so it's exactly delta t naught, the proper time, because the person on the ground can use a single clock. But the person on this rod cannot use a single clock. No. Why? Because when the front of the rod is passing by, there must be a sensor that activates a clock in front, okay? And it registers the T1, the beginning of this trip. And then when it's done, passing the end of the rod is passing by, another sensor will activate or stop the other already synchronized clock and will register T2. Then this guy will subtract the values taken from a couple of clocks. So this guy cannot use a single clock. And as you see, we cannot say that always a person who is traveling will measure the proper time. No, it depends on the event. What do we mean by the event? Now the event can be measured by a single clock from the observer on the ground. So this guy will measure the proper time. Okay, a very nice and important question. Is there always a proper time in relativity? I mean, if we consider a problem, one of the observers will always measure proper time and the other dilated. The answer is no. I will tell you why. There are some cases that you don't have any proper time according to these two observers. Let's say we have the Earth and a planet P, okay? I send a radio signal from Earth to the planet, okay? So the event is traveling from Earth by this radio signal to the planet, okay? This person on the ground will use a clock for finding the embarkation moment and then the arrival, T2, and they will subtract these two values to get or measure the time interval between the beginning and the ending point, okay? This is going to be delta t and the dilated time because they used a couple of clocks, okay? So the ground observer, no, they will measure dilated. What about the person who is traveling with a spaceship? This guy also cannot do that because they have to use a couple of clocks again. He's not going that fast. He cannot move as fast as the light. So he has to use the same procedure. Might be a different time. We will tell you what that time is and how it's related to the time measured by the ground observer. We should learn the Lorentz transformations in upcoming videos. But however, this guy also will use a couple of clocks. So even when you are traveling very fast using a spaceship, for this specific event, you cannot measure the proper time. The answer so is no. You won't expect always to attribute the proper time to one of the observers. No, it's not definite. Sometimes yes, but it's not always a yes answer. Thank you for watching this video and thank you for being with me.